Welcome back, everyone, to the next lecture on the same topic that we have been working on, which is accelerated data analytics. Our previous lectures, the last lecture that we did, was dedicated towards using the cuDF, which is the CUDA-related data frame environment, to accelerate the first stage of the overall data analytics pipeline. Today, we are going to work on additional, I would say, the stages of the accelerated data analytics pipeline. The second one in this pipeline is acceleration of the machine learning algorithms themselves, followed by the last one, which is the acceleration of overall task, not just on one GPU, but across the whole system. So let us get started. Hopefully you remember the overall stack that we saw last time. And today we are going to concentrate on the second window, as you can see here, which is the machine learning part of it. So we had seen the overall scenarios under which we want acceleration. We talked about relationship of the increasing dataset size to the amount of computation power which is required. And if I talk it from a point of view of data science perspective itself, it is generally recommended to start with as much as data as possible and then keep on reducing that data and explore possibilities to pre-process it or scale to meet the performance demands, because it's a known fact that the data sets keep on increasing, but then we use different techniques to reach a particular level where we are saying that we are able to meet the accuracy to the speed that we want to deploy it in the real world. So we start with the larger data set, we apply certain pre-processing techniques, maybe create histograms or distributions around it. We apply techniques which will reduce the overall dimensions. We only select the features which we feel are important, which are giving us really good accuracy levels. We try to remove as many outliers as possible. We may in fact remove certain samples and only have at a particular frequency. And if you see, this is basically the whole objective is to reduce the overall time as much as possible, but without having to sacrifice on the part of I would say, so to get as much as accuracy as possible without having to sacrifice on also taking a lot of time or the speed. But the critical thing here to understand is, no matter what we say, it's an iterative process, and what you require is basically something which helps you in this iteration as fast as possible. So what you're trying to do is you're trying to do basically validation and grid search and do a lot of iteration to go through this overall process. So to solve one of this problem, we are talking about accelerated ML technology stack. Again, at the bottommost layer, what we have is CUDA, which is Compute Unified Device Architecture, which is the GPU architecture which exposes parallelism. Over that, we have a couple of libraries. As we said last time also, like similar to cuDF, these libraries are primarily written in C or C++. Thrust, which is a library for which is a STL equivalent on GPU, standard template library running on the GPU. We have different other libraries like NVGraph for doing graph related problems, and cuRAND for random number generators, and many more. cuBLAST for basic linear algebra operations, and so on and so forth. Over these basic libraries, you have higher level libraries which kind of provides cuML related primitives or algorithms, which are still C++ based, and then these are exposed to the Python programmer, which is the primary language in Python for all of the data scientists. in form of wrappers. So basically, they will internally use Python to basically call the ML based algorithms which are there. So the stack which we showed in cuDF, it is kind of similar here as well. We are having the bottommost layer or parallel computing. Above is the C++ libraries because it is the most prominent one, giving the highest amount of performance. And then the Python basically is calling those C++ libraries using the Python bindings. So let's look at an example of the rapids, and in this particular case, we are still using a C++ equivalent version, which is sklearn, you can see here, or scikit-learn, which is the most popular machine learning package, and we are using pandas here. So we are creating, this is more of a clustering based thing. So you can see here, you are you're creating the pandas, and then you call the sklearn clustering algorithm. Here we are using dbscan, and we do the fit predict, which kind of highlights the two clusters which exist at this particular data set that we have. But just to highlight, there is a small change. We are going to look at a realistic example in the Jupyter notebooks, like we showed it to you last time. But in short, what we are trying to say here is that the idea behind rapids is that there is minimal change in the libraries calls or the source code that you write, which are traditionally being written using sequential or a CPU based platform, and you just have to change import, and you have to change very minimal changes you have to do to your code to make use of GPU. So only here you can see there are only 2-3 changes that you need to do. So over time, cuML has evolved. I think it is still having a subset of things which exist in scikit-learn, sklearn. You have different examples for classification or regression. You have APIs for inferencing, pre-processing. Also, you have APIs or algorithms, particularly in the clustering algorithm or dimensional reduction, or to handle time series data. And we are also going to look at an example of hyperparameter tuning and cross validation also in the demo that I'm going to show you. So Rapids is an evolving, I would say, initiative, open source initiative. There are many algorithms which are already existing, and many keep on getting added over time. So this might not be the complete list by the time you are actually going to use it, or by the time I'm showcasing it to you, and more algorithms would have been added by this time. So it's always recommended to go to the open source project and see which all machine learning algorithms are supported. But in to show you certain examples, like we showed it to you last time also, this is an example of forest inferencing. And you can see here, this work is basically an output of 100 million forest inferencing done for different data sets. And you can see here the time taken by the GPU versus the CPU, and how much speedups you can expect while running only the machine learning part. I'm not talking about the overall pipeline. Yesterday we saw the initial part of data frame and how you can do those pre-processing quite efficiently using cuDF. This is accelerating only the cuML or the machine learning algorithm part in general. The good part about Rapids and is also that it is integrated with most of the cloud ML frameworks. So if you're using any of the cloud frameworks, you can go to rapids.ai HPO, and you can basically look at where all this acceleration has happened on, say, Amazon SageMaker, Azure ML, or Google AI platform. And you can go to github.io rapids AI cloud ML examples to see how to use this in different platforms. Primarily here you can see the three key platforms which are there. So there's an integration of Rapids which has already happened in all of these platforms also. So this is another example again. This is a 100 job random forest airline model. You can see here uh, one of the critical thing that I mentioned some time back also to you is the artificial intelligence is not just about improving accuracy, but showing the return on investment overall. And this is one of the most critical thing is to see that if you were to do a particular training for different, here you can see the airline model of 100 job random forest, and if you were to do it on a platform which is pure sequential, and you were to charge on, say, the same on a cloud based scenario, and they may be in different cloud models. Here you are seeing an example of Azure ML versus if you're spending the same effort and running the same thing on a GPU based system, what kind of return on investment that you can do, or how much money you can save when you're deploying your model. And that's one of the most critical thing which is very much prominent why accelerated computing is also required about having a real world impact. And as I told you, from a point of view of ML algorithms, this is just a list of some of those. When I talk about the functionality, some of those functionalities are primarily supported on single GPU, which means it will run only on a single GPU, while some of them are supported on multi-node, multi-GPU environment. So even if algorithm support is there, it is always good idea to see if the functionality supports single GPU or multi-node, multi-GPU kind of environment also. And this list keeps on changing. As I said, we are in 2022, and this already this particular support for other cuML based framework and also multi-node support might have already been established at this particular point of time. I also wanted to highlight one more part here, which is cuGraph. So if you remember, we showed you the overall. There are different components inside Rapids. One of the component there is also in case you are working in graph analytics. In that case, there is a support inside Rapids for cuGraph library. And the idea is basically to make use of GPU computing for solving graph problems. And you can see here that you can do 500 million edges calculation on a one single GPU of 32 GB, and it can support billions of edges in a multi-GPU environment as well. And it is seamlessly integrated with ODF and cuML also. And there are various algorithms which are happening, but it is equivalent to the NetworkX API, which is one of the most popular ones for graph analytics in the sequential world. And again, it has the Python equivalent for NetworkX, but lower level, at the lower level, it calls the C++ API. Same thing like we saw for cuML, there is the same stack which exists. At the lower level, you have CUDA architecture, you have the CUDA libraries, which are primarily C++ libraries. And then there are DAS-based or ODF-based extensions for the graph, which finally uses Python to call the C++ APIs that we have. And there are various things you can do with it. It's again community based, and you can create different kinds of components like strongly connected, weakly connected. You can do various kinds of analysis, which if you are working in this field, you know, like creating page ranks, right? Or if you would like to do traversals like shortest path, breadth first search, and various other kinds of things are possible for doing graph analytics. There are various things which are already there. There are more which are coming, and it will be supported in the future as well. But you can see the kind of speed ups that we are expecting here for different kinds of routines which are present in the NetworkX. And you can see here that we are talking about speed up numbers, performance speed up numbers in few thousands as compared to few hundreds also. So we are looking at numbers which can accelerate the graph analytics at few. You can see here up to 11,000 also for certain data sets which are available. And again, the same thing. There are various kinds of algorithms available. Sorry for the font, which may not be visible to you, but it kind of highlights various kinds of algorithms used in graph analytics, like page ranking, breadth first search, and spectral clustering, and various other kinds of methods which are there. And again, there is support for some of them on single GPU, some of them are supported on multi GPU within the same node, or some of them are also supported on multi GPU, multi node. So with that, let me quickly just highlight the part of showing you a demo. So just give me a second and I can bring it back to you. So like last time, I have already run the container, the same container which I had run last time, and it is running inside the Docker container, and I am exposing it to 2 GPUs. So I'm going to just go ahead and just refresh the scene just to make sure that it is still connected. So yes, it is still connected. I have my Jupyter notebook, and let me see how many GPUs I have at my disposal. You can see currently I have exposed only 2 GPUs to it, which is of Volta architecture, Quadro GV100, and there is currently no process running on it at this time. So yesterday we saw a hands-on of particularly cuDF. Today I'm going to show you certain characteristics of how to use cuML. So for cuML, as I said, it is primarily a replacement or the accelerated version of scikit-learn, and this is what I'm going to show you. So the example that I'm going to show you first is a simple linear regression example. Then we will enhance it and we will end up the cuML documentation with how to do hyperparameter tuning using, say, a grid search algorithm as well. So again here, this is a simple example of CPU where you have imported NumPy, matplotlib for visualization. And if you can see here, what we are doing is we are trying to create a data set which kind of adheres to the linear relationship. So we are just creating some random values, but they are kind of linear in nature, having a linear relationship to each other. And let us just plot the values. So you can see here, this is our actual true relationship. And we have also added some noise to it also. So you can see here, we have added some noise to it also. So you will see the empirical data points around it. But this is the true nature of the relationship that is existing based on which we created the data set. So what we are looking at is, obviously we know it's a linear relationship, and that's why we are going to use the linear regression, which is primarily a class which is implemented both in the CPU version of it, which is the scikit-learn, and also the cuML version of it. But what we have to understand is, whenever we are using any package behind the scene, every module can offer different kinds of algorithms to solve the same thing. Even for linear regression, just to give an example, like for cuML, we basically provide 3 algorithms to find the relationship. It may use singular value decomposition, it may use eigen method, or it may use a coordinate descent method to fit the linear model, right? And this is very, very critical to know, because when you start moving your model from, say, a scikit-based to a cuML, the default algorithm which are chosen by the cuML might be different from the sequential version, and you might get certain different results as compared to what you would see in the sequential algorithm that you are using. Like for cuML, basically we find that SVD is more stable, generally found out, but eigen is the one which is the default, right? Because it is much more faster as compared to, say, doing a SVD based thing, right? So these are just certain example of what happens behind the scene. By default, you're going to use some default versions, but you can override it to use the same algorithm behind the scene which you have been traditionally using, right? So here, as you can see, we are importing sklearn.linear model and importing it as linear regression. We are creating an object of it. And if you have been working in this field of machine learning, generally we call a fit function. The fit function is the one which is going to basically find out the relationship or the parameters, and it is going to do the training part of your cycle of artificial intelligence. So you do the fit function first, and then you use predict for seeing how well your model have actually learned. So you can see here we are calling the fit function on the data set that we have. And in the end, if you want to see, so what we are doing is we are creating a new data again for inferencing or for testing the relationship. And so once we have created the new data, so we are using the linear regression dot predict to see how well our data can predict the newer data set that we are exposing it to. So we have predicted the value, and finally in the end what we will do is to use matplotlib to scatter and see how well our sklearn is able to predict. So as you can see here, there are three things. One is the empirical data points. The second one is the true relationship that we know already exists, which we had proposed earlier, which is the black line, which is kind of almost completely hidden with the predicted relationship, which is the sklearn based predict value. So you can see here the predicted value and the true relationship is kind of almost overlapping with each other. Hence, we can say that that they are actually doing a good job in terms of predicting for the test for the inferencing part of it. Now let's move towards. So far we have been running it on the CPU. Now let's do the same thing on the GPU. The idea is to have the code which you have seen earlier almost similar, as much similar to the sequential world. And so we are importing cuDF that we have seen last time also. So we are creating a cuDF data frame. Why do we create in cuDF? Again, as we have told earlier, cuDF will basically allocate the memory on the GPU, and you will be basically doing stuff on the GPU. So ideally we should be passing it a cuDF expression. And again, like sklearn, instead of using sklearn.linear model, we are using cuML.linear model, and we are basically importing it. And as I told you earlier, it accepts various parameters, but you're going to use the default version. But you can override it. Like the algorithm that you can use is the eigenvalue or the SVD one. The default one is eigen. If you want to set certain additional parameter like normal, do you want to normalize the data, or if you want to do fit intercept and all, by default it is true. If you want to correct it, then you can also set it to false. So there are different parameters. By default we are using the default ones, but if you would see that your linear regression of scikit-learn may use something else, while ours will use a different version, and you might see different accuracy levels. So just take a note of it while you start putting your data to this, right? So we have kind of trained the model, and what we are doing here is we just want to basically set the points, and we want to just visualize it. So I'm going to not spend some effort in explaining. So what we are doing is we are just predicting the values. So we are creating the new data set for it to be predicted, and then we are doing the prediction here for the test data set that we created. And again, we are going to just do a visualization just to see how good or bad our inferencing is doing. So again, you can see here now, so we have 4 data set points now. The blue dots are basically the empirical data points. The black is the true relationship based on which we know we created the data set on. You can see here that the predicted relationship of the CPU, which is the red, and the green one, which is the predicted relationship with respect to GPU, are almost overlapping with each other. In fact, I don't even see the red bar, which is the CPU version. It is behind the green bar. So in short, that the red and green lines are identical, which kind of states that both cuML and the CPU version, which is the scikit-learn, both ended up with the identical models, exactly what you would have expected, just that it was running on the GPU and it will be much more faster. So this is the ridge expression, which is an extended version of linear regression, and it kind of helps by providing you L2 regularization, and it can predict linear combinations quite well because it basically reduces the variation. And so we are not going to cover the part of what ridge expression is, how is it good. We are not going to cover that part. But the reason why we wanted to show this to you is to tell you that there are so many parameters which exist, and how the relationship of parameters can change the accuracy levels when you move from one framework to the other. So here again, we are importing sklearn, and we are loading a particular data set, which is a diabetes data set, which comes with it. The diabetes dataset basically consists of 10 base variables. It consists of age, sex, body mass index, average values, and it also consists of 6 blood serum measurements which are there. And it has basically 442 rows for different diabetes patients. And also it has the value for the response of interest. And what we are trying to do is to see, what we are trying to do is to find a quantitative measure of the disease progression 1 year after the baseline. So that's what we want to predict for this particular data set. So again, it has 442 different patients. It has 10 attributes. The 10 columns are basically the numeric values, predictive values, and also you have the 11th column, which is the quantitative measure of the disease progression 1 year after the baseline. So this is the data set, and you can find more details of the data set if you require here in this particular link. But let's get the data set, and then we split the data set into training and the testing part as well. So we are just doing a train test split, and as you can see here, instead of just importing a normal linear regression, we are importing the ridge algorithm here. And the ridge, as I said, kind of does a lot of things. It has various classes inside, like the alpha value can be the float or double. It kind of defines the regularization strength, and you can define it as a positive value. The larger the value specifies the stronger regularization, right? You can define the solver to be either eigen, SVD, or CD, like the linear regression. And you can also define other things like whether the predicted values are normalized or not normalized. By default, it is kind of false. So once we have defined this, let us try to create the thing and just try to make it work on the CPU as well as on the GPU. So what I'm doing is I'm just copying pasting the solution for scikit-learn again. So you can see here I'm calling an API called as skridge, and I'm giving it certain parameters which are by default, or I'm overwriting it. So you can see here I'm giving it a particular alpha value which I have taken, which is 1.0, and I'm also saying the solver that I'm going to use is Cholesky instead of the default one which is used. And I can just do that expression, and the same thing I'm going to do for a cuML, but I'm going to use different parameters here in the cuML space. So in the cuML, my alpha value is the same, but I'm saying that I'm going to use a different solver, which is eigen, instead of using a solver which was Cholesky here. So let me just run this particular part, and then what we are going to do is we are going to just we are going to measure the accuracy levels at which we are able to predict the values. and for which basically there is a class which is called as score, which is used to measure the performance of the ridge expression. So let me just try to do the same thing for both sklearn as well as to calculate the score, basically kind of saying how well our model does on the test data set. So in this particular case, you can see the scikit-learn accuracy, the score is 0.1586. Let's do the same thing for cuML as well and see how well it performs. I'm sorry on this part. So you can see here it's almost the same. You can see here it gives 0.15868073. To a large extent, both of them are giving the same results. But if I change the value for something else, maybe instead of using eigen, if I say use SVD, we might start getting different results here. So let me again run this range expression. I have run it for specifically for the cuML part of it. And let me just again create this. And you can see here it has slightly changed at the few decimal places later on also. So, but just to show that there are different kinds of hyperparameters which exist. But the good part is that you can actually select the hyperparameters, or you can do a search for the hyperparameters and improve the accuracy of your models. And for this particular case, we are using a method which exists in scikit-learn, which is the grid search CV. It is present in the scikit-learn, as the name suggests. It will do a grid search for values for the parameters that we specify. Like in this particular case, I am saying that I would like to search within a parameter space for only alpha. So I'm saying that I want to do a grid search, which alpha values is more better for me. And there are different methods. You can also add other parameters also, like you can choose whether you want to try out different versions of the solver, or you want to just try out alpha. So you can add as many parameters as you need that you would like your grid search to basically figure out to and spit out what is the best method, or what is the best value which it is going to give out. So you can see here that I'm trying to do the grid search CV, and it is going to spit out what is the best score for which particular alpha value. So here you can see here that it did a search for different alpha values, and it figured out that 0.001 is the one which is having a much more better score as compared to what we saw earlier. If you remember, the score there was 0.1 something. Here the score is much higher, which is 0.48. And then we can do the final fit to see that in fact for all the test data, if we are getting the best results or not. So this is the same thing that you can do once you are done with the grid search. Then if you want, you can provide the same to cuML as well. Do the grid search for cuML and find out if it is indeed giving the so it can see here the same grid search. 0.01 is the best alpha value according to it, and it is providing you a score of 0.48. So like in deep learning, even for machine learning, you can use some of this hyperparameter tuning methods like grid search and try to find out which hyperparameter works the best for the problem statement that you have in mind. So this was a very quick demo for you to understand the cuML and how cuML is very similar to if you were running on a sequential environment using scikit-learn. You just have to import the right package, and you have to take care of additional things like if you are using the right hyperparameters or not, because there will be certain changes in accuracy which can happen.